Okay, thank you so much. I think we are 5 minutes above, so I will try to do my best to catch up the time. Today, I'll be talking about how we can use AI and computer vision to basically quickly and safely check the serviceability of bridges and specifically reinforced concrete bridge columns. And that would be the topic of my presentation. Let me first thank the sponsors of the project, Detroit Lee through UTC and South Dakota State University for providing the match for the project. So you might all know that the current design philosophy in AASHTO is that it is okay that the bridge after moderate to severe earthquake get damaged, but it's not okay it collapses. So based on this design performance, it is totally acceptable that bridge columns get damaged. Why columns? Because columns are by design the weak link in the overall bridge system. So after an earthquake, tsunami, or something big, if there is any component that is allowed to damage, that would be column. We had hard time to find actual earthquake damage of real bridges in which the columns are designed by the modern codes. We were able to find a few in Puerto Rico, and let me thank Dr. Cole for providing those pictures. That was nice of him to share those pictures with us. So it's totally acceptable to see these damages after the earthquake, but the question is, will these bridges be serviceable? Will you allow all traffics, only first responders, or you will close the bridge if you see damage like this? Another issue is that every single bridge needs to be inspected by trained personnel. So every single of those need to be carefully basically checked after the earthquake. So you need an army of engineers to go there after a big event like earthquake and check all of these. So that would be very time consuming and may take a day or two to inspect all of these bridges while people are still passing through. So the main goal of the project was to see if we can use computer vision and AI to expedite the inspection, particularly for the earthquake and for reinforced concrete bridges only and modern ones. So I'm not talking about those columns that are designed before 2000. So anything afterwards will fit into this basically software that we developed here. And the goal is to have a mobile application or mount that software and drone. So if you have local personnel available close to bridge, rather than sending the bridge engineer, that local personnel can go basically take pictures, perform analysis right there, and comment if the bridge should be open or closed and do the necessary action. So that was the whole goal of this project. So I will keep this one short. We started with the literature review. The first thing that we found was that visual assessment after an earthquake is the first choice by any DOT that has earthquake. So they do not use sophisticated tools like a radar or thermal cameras or anything like that. They don't do that because they want to go and access the bridge fast, quick, and take an action there. And there is no national specification. What you need to do after an earthquake and other big events, how to evaluate bridges and make sure that they are okay and serviceable. However, there is an NCHRP report that does that and provides 4-level damage assessment. They call it fast reconnaissance. So this one is done by airplane. So you fly around all of those affected sites. You see if your bridge is washed away or totally collapsed or not, and then send people. So that one is very fast. Then preliminary damage assessment, you really send the person to site to inspect the bridge, comment on it. Detailed damage assessment involves also structural analysis, and the extended investigation means it 2-3 months after the event, there is a full engineering work from geotech to structural, say if this bridge is okay or has to be basically closed or like replaced. So there are 3 tagging involved under each of these category. Red means the bridge is no good, you have to shut it down right away. And yellow means only first responders can use it for a while. And the green means everyone is allowed to use the bridge. So the timeline is very important, and tagging these color coding is very important too. So we adopted this NCHRP report that was not just for bridges, that was for all transportation infrastructure, but we adopted that for just bridge evaluation as well. The first, and later also in the literature review, we have found that the definition of damage and damage state that we have for reinforced concrete bridge columns is more qualitative. So they will say, if you see this crack, do this, or call it damage state 1. If you see yielding, you cannot see really yielding, it's damage state 2. And if it's totally collapsed, it's damage state 6. If you want to program this, computer doesn't understand any of those. So you need a measurable values so computer can see, measure it, calculate it, and comment on the damage state of the bridge column. So we keep those 6 damage state that is practical and is used by Caltrans and basically other states, but we provided a quantitative measure for each damage state. So damage state 1, just to save some time, I will show 1 and 6, the best and the worst case scenario. Damage state 1 means you see a few flexural cracks. Few examples are here. And the way that we define it is if your theta, which is the angle of the crack with respect to the vertical line, is more than 80 degrees. And damage state 6 means it's bad, it's gone, you need to replace the bridge, red tag it. And the way that we will basically define it is based on the number of exposed bars. So just like a few examples to show you how you can program these damage states. And in the next step, we found that if you want to correlate that those damage states to a displacement during an earthquake, you need a database of reinforced concrete bridge columns. There are a few database out there, but we have found that they are mixed of buildings and bridge columns. We also found that they include both substandard, those old bridge columns, and new ones as well. And we also found that any test data beyond 2008 are not included in those databases. So we made our own database. The new database includes more than 220 basically circular columns and 68 rectangular columns. And we collected 34 parameters per testing, and we put them in a spreadsheet for everyone to use it. And all of these definitions like axial load, cover concrete, and yielding, stuff like that, all are based on AASHTO. So that's the language that every single bridge engineer will understand. So we try to tie all of the definitions of this spreadsheet to AASHTO. Now, this document is public. Feel free to download it through the Design Safe data depot, and feel free to use it in your applications if you have. The big question is, most of the bridges in the US, they are not instrumented. Means that if there is an earthquake, we absolutely have no idea how much they displaced during that earthquake because there's no sensor. So we need to find a way to estimate the displacement demands, how much the column moved during that earthquake, to be able to successfully analyze it and say it's okay or not okay. So the AASHTO seismic guide provides three methods. I'm not going into detail. One is a static method, and then linear elastic method, and a linear time history analysis as well. So there are few tools out there for us, but these are at the design time. If you want to design a new bridge or check if that's okay, but not for after the earthquake. So we have proposed a few ways that you can still use AASHTO, but then do it to calculate how much displacement the bridge saw during the earthquake. So number one, we'll use AASHTO spectrum. Number two, there are websites like USGS and a few other that a few seconds after each earthquake, they will give you the ground motion. So we do have programs to convert those ground motion to spectrum. So you really use the site-specific spectrum to check your bridge. Then you have your ground motion. You can really do linear or nonlinear dynamic analysis. And last one is, can you use those pictures that I showed you earlier that shows the damage of the bridge and estimate the displacement just by post-earthquake condition of the bridge? And that's what I want to discuss today very quickly. So I said that we developed our own database of reinforced concrete bridge columns. What we did, we collected any test that is out there from beginning. You can find in literature to 2021. So we do have our test database. We know what is the displacement at each damage state, so we can perform a statistical analysis and kind of relate at damage state 6 how much displacement you will see. It's not that easy. You need other parameters like confinement, axial load, and aspect ratio embedded into your equation. Dr. Eberhard also did a similar study with a much smaller data set with 20 columns. Now we have 200 and let's say 50 columns and stuff like that. So we have a bigger database to play with, but he did the same thing. We followed his equation and kind of developed a relationship between damage state and displacement that the bridge will show you that much damage. For example, if you're seeing a spalling, that means 2% of displacement during the worst time of the earthquake. So we have that. And we also did it for damage state 5. Rather than developing a new equation, we said, let's relate it to damage state 6, so 80% of that. And 4 and 3 and 2, we did another one. So now we do have a statistical equations to relate the displacement during earthquake to the damage that you see after an earthquake. And to prove that, we did a half a scale column testing here at this TSU, and we wanted to check if these equations are accurate. When you use equation to see at what time you will see the cracking, or equation says 0.5 drift ratio. Drift is how much displacement you have normalized to column height, and very close to the actual displacement. At what displacement the column will yield, the measured one was 0.75%, or equation 0.9, slightly off, but still very good in terms of overall estimation. At what displacement you will start see a spalling, or equation is saying 3%, while in our test we saw 2%, some percentage off there. At what displacement you will see damage state 4, a bigger spalling area, 5 and 5, perfect match. At what displacement you will see more extensive damage, or equation is saying 8%, in test we saw 7%. And most importantly, at what displacement this column will fail, or equation is saying 10%, and this column in fact failed at 10%. So now we have 6 equations that will cover the full spectrum of force versus displacement of column. And if you see a damage like this one, you should be able to say how much displacement you had during the earthquake that caused that much of damage. So these equations are set, is out there in the report, and we should be able to estimate the displacement demand by post-earthquake damage. So let me then move on. So I know how much displacement demand I will get by using the picture of the column damage. How about the capacity? The most advanced tool, like what Dr. Pendeltis was discussing in the previous presentation, we can use OpenSeas, perform a pushover analysis, get a force displacement relationship. This is the yield point. This is where the column will collapse or fail. And we are proposing to use pushover analysis to obtain the full picture and have the capacity displacement of the column. So we made a generic OpenSeas model using only 8 column parameters. You can generate a pushover curve. We implemented this model in a basically website, and we're working to make that website public. Should be out fairly soon. And we validated the model by randomly picking 4 columns from database and using these 8 parameters, see how good or bad we are with respect to test data. For posters quick action, this model produces fairly well good results compared with test data. So it's like reasonable and actually reliable. So let me move on to the last component. So we know the definition of damage state. We know how much displacement that column saw during earthquake, and we know the displacement curve and the capacity. So where the computer vision come in? That one comes in to tell you, if you see this picture, rather than a bridge engineer comment what damage state it is, the computer will tell you what damage state it is. To be able to do that, we have used 2 networks. One was the mask RCNN to see spalling rebars, and we use the mobile net version 2 for crack detection. I do not go too much into detail, but let me share with you that we had around 2,000 pictures of our C bridge column in-house. My colleagues like Dr. Pendeltis kindly shared more columns, damage photos with us, so we got more pictures and we start training our neural network with these pictures and with these like limitations that you see here. For example, to detect the cracking, we use 20,000 pictures, almost half of those with cracked and half without, basically cracked, to successfully train the network. Here is one labeling that we manually did, and then later on software was able to see those. I guess here, something new that we did, the determination of the crack is really hard because cracks goes around large aggregates. So, but there is a fundamental or major basically crack angle. For software to see it, we ended up with a histogram. For example, if you see a crack like that, the angle is compared to vertical axis. The software is telling me it's basically 80 degree, very close to what we see in real life. And here is kind of 45 degree. The histogram is telling me the angle 40, 45 is the major one. And we see that here as well. And here is 25 degree again. The angle is with respect to the vertical axis. Very good estimation of the crack angle when you see the whole picture, not just one small portion of the crack. And here are few results of the computer vision tool. When you upload the picture, then it will try to count the cracks for you. It will spit out the number of horizontal cracks, vertical cracks. If there is a spalling not in this picture, it will show you the area of that or maximum length of it, and how many transverse bars you have and how many longitudinal bars you have. If you count all of these, then you should be able to go to damage definition and say what damage state it is. And we checked it with ground truth or actual one, very good estimation of the actual damages. Here are just quick few examples of that. So that's damage state 1, where you have only basically flexural cracks. The computer software, regardless of the shape of the section, will give you the number of the horizontal and vertical cracks. If you have a spalling, it can give you the spall area. If you have exposed bars, it can see all of those exposed bars, longitudinal, verticals, and give you the number for those regardless of the shape of that. And then in overall, in computer vision, they use something called precision and recall to show the accuracy. 0 is bad, 100% is perfect. You can see that we are at all time above 90%, means that whatever picture you upload, it should be able to see the column itself, spalling, transverse ball, longitudinal balls, and cracking with very good confidence and accuracy. So I will end my presentation with this basically flowchart. I told you earlier that there are 4 steps of post-earthquake evaluation. First one is by the airplane, not that one, but number 2 and 3, preliminary damage assessment and detailed damage assessment. How you are going to do that using the tools that we developed here. So if you want to do PDA, preliminary damage assessment, take picture of the column, upload to this computer vision tool. It will tell you what damage state it is. If it's damage state 1, 2, 3, it's good. 4 limited, and 5 means and 5, 6 means close the bridge. As easy as that. So you just need pictures of the columns. Then if you want to do more detailed analysis, detailed damage assessment, you need to first perform a pushover analysis. Now we have a tool for you. With only 8 column parameters, you can get this chart, force versus displacement, what displacement will fail. And then you also need column pictures to fit into the computer vision tool. It will estimate the damage state. There are equations that as I showed you earlier. If you see damage state 2, what is the displacement associated with that? So you know that 2, you come here, map it on your force deformation chart. And if this point is within this chart, you're okay. If it's outside this chart, means the column is bad, and then the bridge needs to be closed. And we set a few, let's say, safety limits on that. It depends on where this point is compared to last point. You can comment on the serviceability of the bridge. So with that, I will end my presentation, and please let me know if you have any questions.
Very impressive. Very impressive. I like the systematic approach to this, very important issue, especially we're dealing with multi-hazard, and I think this will really benefit quick recovery and better resilience.
Thank you. Yes, and that was the whole idea behind it. Yes, thank you.
So Mostafa, let me ask you a question. Is it
Sure.
possible that sometimes the pictures don't tell the whole story?
Yes, because if you take a picture from the side that there is no damage, then your bridge is okay. So our idea is the person that you are basically sending to the site takes multiple pictures around the same column. So if you're seeing the whole picture, then you can and basically upload 10 pictures of the same columns, then it will find the worst one for you.
And did you
Perfect
find,
question.
yeah, thank you. Did you find that the picture tool, the vision tool, sometimes will contradict the pushover tool?
They are not really related. So one is trying to do is to get the displacement demand, and pushover is just to give you displacement capacity, like what OpenSeas does. So we are basically using OpenSeas.
Do they always agree though? I mean, maybe the vision tool tells you one thing and the other calculation may not agree with it.
The only check that I did, or we did 2 checks. One was the database. So you have 300 columns, then you do a statistical analysis, that's your accuracy. And the single column that I actually showed you, the 6 damage states, and they worked fairly well. Might be a case that is slightly off, but we try to have a conservative equation. You want to have a safe bridge within a few hours, and then after 2-3 days, trained personnel can get there and they can comment on that. You want your local folks to comment on the bridge fast and quick.
So my advice to you here is don't be too conservative.
Okay.
Because it will give you the opposite result you're looking for.
Okay, yeah, sure, absolutely.
Okay.
And I just want to mention that we are trying to mount this on a website. We do have it on a laptop. The website is basically designed on a local server, but we're trying to put it on this CSU server. Right now, the analysis like this will take a minute when you upload a picture because you're running on a laptop, but we're asking for kind of commercial level, basically servers, so that would reduce the time of the analysis significantly. And you can also perform the OpenSeas analysis in this website as well, just by providing those information.
Very good. Excellent. Thank you.
Thank you so much.